Taking a look at writing net ionic equations today. Before we get started, let's define qualitative versus quantitative analysis. Qualitative analysis means what is present. It's an identification based on observations only. Quantitative tells us how much is present. This relies on a measurement or a calculation so that you know the actual amount of something present. So qualitative is based on observations, quantitative is based on measurements. Examples of qualitative analysis that we've actually looked at, conductivity, so ionics and acidics conduct, our molecular don't. We've used litmus tests for acids and bases. We've used solution and flame colors. We've done a precipitate test. We've decided if something is soluble or insoluble in water. And we've seen reactions with metals. So dropping a piece of magnesium into an acid, it will bubble. Nothing else will it bubble with. Those were all based on observations. Quantitative is based on measurements. And we get to a lot of these in our next unit for stoichiometry. But crystallization, so leaving the solid behind by evaporating the solution. Filtration is kind of like a coffee filter. We take the solid and leave it in the filter and let the liquid run through. Gas collection, we can collect gas in tubes, just kind of catching the bubbles, if you will. A titration is something we'll look at, but it can tell us the concentration of an acid or a base based on a neutralization reaction. And data using graphs or calculations, we can calculate anything. From these, for instance, crystallization, filtration, we could weigh the mass. For gas collection, I could find the volume of gas collected. For a titration, it gives me a concentration. And data analysis can give us a variety of different options, but these all give us numbers. A net ionic equation is a chemical reaction that includes only those things that react and omits anything that doesn't actually change within the reaction. So a spectator ion is something that doesn't take part in the chemical reaction. It exists as both a reactant and a product, so there's no change in its state or its charge. And that's the deciding factor here. There's no change in the state or charge for it to cancel and be a spectator ion. Steps to writing net ion equation, we're going to write a complete balanced equation with states. And we are going to dissociate all soluble ionic compounds and ionize all strong acids. So this means we're going to, break up soluble ionic and strong acids. Things we're going to leave together are moleculars, weak acids, and insoluble ionic. So we're looking at a dissociation. We're going to cancel things that appear on both sides that are identical. So state, charge, etc. has to be the same. And then the net ionic is just what's left over, and the spectator ions are what we've canceled out. Easiest way to see this is to practice. So student mixed solutions of lead 2 nitrate and sodium iodide and observed the formation of a bright yellow precipitate. What is the net ionic equation? So the first thing we need to do is write a full balanced equation. Balanced equation. So lead 2 nitrate, PbNO3 2, which is aqueous because it's a solution, and potassium, it's sodium, NaI. So it's a double replacement, so we're going to make NaNO3 and PbI2. When we look at our solubility table, NaNO3 is aqueous, PbI2 is insoluble. Balancing, I need a 2 here and a 2 here. Our ionic equation is when we have broken up anything that is a soluble ionic. So the soluble ionics in this case are PbNO3 I can break up, NaI I can break up, NaNO3 I can break up because they are soluble and ionic. AKA, if I were to look in on their solutions, they would just be ions floating around. So let's dissociate those into its ions. We have Pb2 plus ions, and we have 2 NO3 minus ions because of this 2 here. Then because of this 2, I have 2 Na pluses and 2 I minuses. And then I'm going to get 2 Na plus, 2 NO3 minus, and then still stuck together is PbI2 as a solid. So you can see things that are identical on both sides. We can see that Na is the same on both sides. We have 2 of them, so we can cancel both because they are both a positive charge and aqueous. I can also cancel in that same idea the 2 NO3s. But because I don't find Pb2 plus by itself or 2I minus by itself, they come stuck together. Those don't get canceled. So our net ionic will be just what's left. So Pb2 plus and 2I minus, making PbI2 solid. So this shows that the ion Pb2 plus from our lead 2 nitrate and the I minus from sodium iodide combine to make the precipitate PbI2. The last thing we were asked to do is write the spectator ions in our notes. Spectator ions are ones that got canceled out. So we canceled out the NO3 minus and we canceled out the Na plus ions. Those were spectators. They didn't change. They started as an ion and ended as an ion, dissolved in water. Let's try one more here. For this, I would get you to pause it and just check your work for each step. So the first one, you're going to write the balanced equation. So pause the video and write the balanced equation for the reaction of zinc metal in aqueous 2 copper sulfate. Okay, hopefully you got the same equation, making sure that your states are the same. Now we get to only dissociate or break up any compound that is soluble or ionic or a strong acid. So in that case, we get to break up the CuSO4 and the zinc sulfate into their ions. Pause the video now and write the full ionic equation. Hopefully we got the same thing here. Again, being sure that you have states and charges for anything that was ionic, considering like a dissociation equation. So zinc stayed the same because it would not dissolve in water. Copper sulfate is dissolved in water, so if we zoomed in, we would see just copper 2 plus and sulfate. Copper stays the same in our products, and zinc sulfate is broken apart into its ions. So from here, we're going to cancel the spectators. The only thing that is the same on both sides is the sulfate ion. We can see that zinc has changed state, and it has become from a neutral element to an ion, and vice versa. Copper has gone from an ion dissolved in water to a solid. So the full ionic, or the net ionic, will be zinc and copper 2 plus ions becoming copper solid and zinc 2 plus ions. And the spectator in this case would be the sulfate. Try this one on your own and then check your answer. I'm going to write out the complete answer below, so pause the video now. Okay, so let's quickly go through this. Our balanced equation shows a strong acid and a base, creating a molecular compound and a soluble ionic. So I have dissociated my strong acid, I have dissociated my soluble ionic, I have kept my molecular together, it does not break apart into ions, and I have dissociated my soluble ionic. From there, I saw that I could cancel Cl and barium, and those are my spectator ions. I'm left with H plus and OH minus making water. You can see that all coefficients in this equation are at 2, so I could technically go in and divide every coefficient by 2 and reduce this to 1H plus 1OH minus makes 1 water. There's something fancy about this reaction. We have an acid reacting with a base. And what we see is that the hydrogen ion from the acid and the OH minus ion from the base react to form water. So the acidic properties and basic properties are neutralized, making water. That gives us the definition of a neutralization reaction. This is a particular type of double replacement where an acid or an H ion and a base, also known as an OH minus ion, react to form water. It also formed a salt. In our case, it was barium chloride, that was not an acid, not a base, and was really a spectator in this entire thing. Okay, so a salt is just a soluble ionic compound. So salt is a soluble ionic compound. So in general, we can generalize that we have an acid and a base. We'll always make water and a salt. So that acid was an H plus, and the base was an OH minus, and this is going to make H2O and some sort of soluble ionic compound. And this soluble ionic compound ends up being our spectator ions. So the full generalization is that the H from the acid, the OH from the base make water. And that's how we get a neutralization reaction.